then q square minus q dot p plus m1 m2 over q square minus m1 square q minus t square minus m2 square. So here we see three kinds of integrals. One kind is d4 q over 2 pi 4 1 over here this part can write outside m1 m2 1 over this quantity here let's call it a and this part b, so we have 1 over ab. The second one is minus of 4 pi minus 4 nc. I can write it q dot p as q alpha p alpha and bring the p alpha out of it. P alpha d4q and d4q over this one 2 pi 4 1 over q alpha over ab, but we know this is 0 because this is a odd quantity and here we have a symmetric limits for integrals, so this will disappear. So we have another integral here. The third integral is d4 q over 2 pi 4 q square over ab. Let's first calculate the first integral or this integral. d4 q over 2 pi 4 1 over ab. You saw in the Feynman calculus courses that we can write the AB as this form. Dx from 0 to 1, 1 over ax plus bx power to power of 2. This is valid for every a and b. You can show it by yourself, doing from this integral over x. And x bar here is 1 minus x. This method is so-called Feynman parameterization method. So let's apply here. We will have this integral that be, for example, I1 integral 1. So I1 is equal to d for q over 2 pi 4. 2 pi 4. The integral covers from 0 to 1 dx 1 ax. What was our a? Our a was q square minus m1 square times x plus b. b was q minus p square plus minus m2 square times x bar. Right. To the power. Now we multiply, we expand this denominator. denominator is q square x minus m1 square x plus q square 1 minus q square x bar plus b square x bar and minus 2 p dot q x bar minus m2 square x bar. Now, here we have q square minus q square x, because x bar is 1 minus x. So these two terms cancel each other. And the remaining part is we have q square minus m1 square x plus p square x bar minus 2 pi p dot q x bar minus m2 square x bar. Now we rearrange it as q square minus 2 pi q x bar minus m1 square x plus b square x bar minus m2 square x bar. Now we can write these two terms as q minus 2 p x bar. X bar squared minus p square x bar x bar. So we squared it and we subtracted this term to get the same result. So minus m1 square x plus p square x bar minus m2 square x bar. Here, now we change the variable from, now we consider, for example, k be q minus p x bar, and e for k is equal to e for k equal to e for q. Since this momentum is constant. The momentum of the measure, but we have a q as variable. Here we change our variable to k. So here for denominator we have k squared, and I call this the remaining part as delta. So my integral is can be written as d4k over 2 pi 4 1 over k squared minus plus delta the power. Now I will use an exponential representation for each one over a over n to the power n. We can write it as gamma n, this is gamma function, and n integral over alpha For example, from 0 to infinity, alpha n minus 1 e to the power minus alpha a. Well, this is okay for all n here, but n positive. Sorry, for n positive. Because n for n 0 and n minus 1, this gamma will diverge. So this is only valid for n greater than 0. You may verify this relation to yourself. Now, using this representation, I can write my integral I1 as d4k. Oh, sorry, here we have also integral over x 0 to 1. So here we have integral over x from 0 to 1 and the integral over d4k over 2 pi 4 to the 2 pi 4. 1 over here we have n equal to 2. So this is 1 over gamma 2. E alpha, alpha from 0 to infinity, and alpha 2 minus 1, e minus alpha times k squared plus delta. We know from the properties of a gamma function, this gamma n equal to n minus 1 factorial. So gamma 2 will give us 1. So I1 will be equal to 0 to 1 x over integrate over d4k to pi 4. Also here we have 0 to infinity d alpha. We have another alpha. Here e to the power minus alpha k squared plus delta. Now I can write it as 0 to 1 dx integral 0 to 0 to infinity e alpha e to the power minus alpha delta and d4k over 2 pi 4 e to the power minus alpha k squared. So this is a Gaussian integral, and you know from 0 to infinity dx x to the power minus alpha x squared. This is square root p over alpha in 1 dimension. So in 4 dimension, we can write it as square root pi over alpha to the power 4. Now, our integral I1 is equal to 0 to 1 dx 0 to infinity d alpha e to the also I write the pi square here out of the integrals, and also I have alpha 4 in the denominator. Here we have alpha minus 3. Right?
Alpha squared.
Sorry, alpha minus 1. This is alpha minus 1. we have another alpha, alpha minus 1. Then e to the power alpha. Now if I change another variable, I consider alpha delta et as, and this is constant with respect to the alpha, so it does not depend on alpha, so d alpha equal to d over delta. So this is equal to, from here I will find d squared 0 to 1 dx 0 to infinity 1 over delta. Also 1 over delta does not depend on d. So I can write it as here 1 over delta 1 over so also here we have alpha. Alpha is equal to t over delta. So I can write it as 1 over delta, and from here we have another delta, maybe cancel each other. And here we have t minus 1, e to the power minus t dt. This is the form of the gamma function. You know, gamma function, gamma n can be written as 0 to infinity dt tn minus 1 e to the power minus t. So from here, this is, here we have minus 1. Minus 1 means 0 minus 1. So when we compare these two, we get here, we see that we have gamma 0. And gamma 0 is not a finite number, so it diverges. So this is those same things. So up to here, I show that this integral has a divergence, and we should separate the divergent part. To separate the divergent part, we go to d dimension. So let's write from here the relation. If t goes to d dimension, yes. Now d dimension. So this integral, this part should is written in this term dd of q over 2 pi d. 2 pi d 1 over ab 1 over q squared. This time I defined I had a definition for delta, which I defined as positive delta. Now I define as negative delta. So we can have such an integral in d dimension. From the same way, if you do this integral, you will have the Gaussian integral in d dimension. And after choosing the integral, you will get this result. I only write the result of this integral, but this is the same as I did in 4 dimension. 4 pi d over 2 gamma n minus d over 2 gamma n 1 over delta n minus d over 2. So this is our result in d dimension. From here also we see that for n equal to 2, which we had, for n equal to 2 and d equal to 4, we have divergence. Now to get rid of this divergence here in 4 dimension, we have n equal to d, and we set d equal to 4 minus 2 epsilon. So this part, this diverged part, here, this is finite. This is finite, only we have divergence here. So this part, gamma n minus d over 2, will give us gamma n, which is 2 minus 2 plus epsilon. So now these two cancel each other, and we get gamma epsilon. But from the properties of gamma function, gamma epsilon can be written as 1 over epsilon minus gamma e, which is Euler gamma, plus part in epsilon. So when we set epsilon to go to 0, this part is diverged. This part diverges, so our infinity appears here, and this part will give us 0. Then this is finite. This is Euler gamma. So by this way we separated our divergent part.
So what is the Euler gamma? The function, what kind of function?
No, it is a number. It has a value approximately 2.771. Sorry? This is a number. If you expand gamma in terms of epsilon, you will get this expression. You may do in Mathematica, and you will get this result. So, also here we have another integral. This was 0. Also we had the third integral which I cleaned. Our third integral was d4k, d4k. If we go to d dimension, d4, dq, d4q, dqq, dq over 2 pi d, q squared over delta minus q squared minus delta to the power n. Now I add a delta, I subtract the delta and add the same to the denominator. So here I will get delta over delta dd q over 2 pi 4, 2 pi d, not 4, 2 pi d, 1 over q square minus delta over n. Here this is integral 1. And also another part. Now we can simplify denominator and denominator for this part, and we will get dq over 2 pi d. This time 1 over q square minus delta is delta to the power m minus 1. To the power m minus 1. So using this expression, which I wrote here, you also can find the result of this integral by replacing n by n minus 1. Also, we also here we have this integral also. This has a diverse part. Well, so our amplitude has 1 over epsilon part 1 over epsilon plus a finite part. Now, up to here I showed how we separate the divergent part. Now in our calculations we have another diagram. Sometimes adding the amplitudes of diagrams cancel these infinities. So, for example, when another diagram sometimes comes in minus 1 over 3, 1 over epsilon. So these two cancel each other. But sometimes we have no such situation. We have a divergent part, but in our calculations we have some transformations. For example, in QCD symbols we have Borel transformations to remove the contribution of the higher states and continuum and isolate the ground state. The Borel transformation, for example, is if we apply the Borel transformation, I will not discuss. For polynomials, we will get 0. And for constants, it will give us 0. So if we apply the Borel transformation in QCD symbols, we will get also the finite result. But if not in QCD symbols, in other ways, under other calculations, you may have also some diagrams which cancel the divergent part of each other. So, can stop here. Do you have any questions? Any questions?
Why that the higher corrections they will cancel this divergent part?
Because in the experiment we detect the ground state and we deal with the ground state. For example, if we want to calculate the mass of a meson, we calculate the ground state mass. So we should remove the contribution of higher state and continuum, and you will see the details of the method next.
Let me make a short reminder about this evening. We will have dinner here at 7.